don't see any. Leslie Lamport is, until today, was for me just a name in the literature and source of many intriguing and interesting papers on distributed systems, time synchronization, fault tolerance, and so on. And it was with a great deal of pleasure that I learned that he had joined the SRC along with a number of other esteemed people who also had just been names before they became digital people. So what I'd like to do without further ado is to turn things over to Leslie Lamport, who will be talking about taking a snapshot of a distributed system. There it is. I knew there was a camera somewhere.
Okay, is that working? I guess, let's see, I suppose that should be projector number 1, moderately in focus. Probably be best if we could have the lights a little lower. Is that possible? Okay, I'm describing work that was done by Manny Chandy and myself. Makes it sound very serious professional work being done. It turned out that I was visiting Texas a couple of years ago, and Manny and I went out to dinner, and he posed this problem over dinner and a bottle of wine, and it was clear that neither of us were about to solve the problem that night. The next morning, we had both of us walked in with the same solution. And the problem is, in fact, very easy once you formulate it correctly, or once you understand exactly what the problem is. And so most of this talk is going to be devoted to sort of telling you what the problem really is. And once I've done that and really showed the theory behind it, the algorithm will be almost self-evident, I hope. Okay, the problem we'll assume the usual sort of simplifying assumptions, namely a network of processes with lossless, unidirectional, buffered, first-in, first-out channels. And for example, here's a network of 3 processors with the channels. And the example I'll use is an almost invisible funds transfer problem, where also the point of this, each process has a state, and that state is changed by events. And there are 3 kinds of events: send message, receive message, and a so-called internal events that consist of the process simply doing something without any message being involved. And the example I'll use is a funds transfer system, where there are 3 processes. So each process represents a branch of a bank, and the state consists of the amount of money that's in each branch. It's the state of each process. And processes send money by sending messages. So here's a situation where, for instance, there's $80 in this bank. It's a small bank, and it's just sent a $25 message from this bank to this one. And similarly, there are 2 messages, a $20 and a $10 message. And when this message arrives, the bank will pocket the money, and then there'll be $75 in that account. And the basic idea that you want to do is to find some way of finding a global state. Now, there are a lot of problems involve determining the global state of the system. That is, you'd like a system like this may represent 3 branches, one in, let's see which way, this is west, California, Chicago, and New York. And you'd like, say, to know the total amount of money in the bank. And so you'd like someone to be sitting up on the moon somewhere, standing back and taking a snapshot of the entire system so they get a picture that looks something like this. Well, the problem is that there's nobody at the moment sitting up in the moon, and the best you can do is you can have somebody in Chicago taking a picture of what's happening in Chicago, and somebody over in New York taking a picture there, and so you'll get a whole bunch of local snapshots, and you have to somehow put them together to get a picture. And the question is, how do you do that in such a way? I mean, clearly, if the person in New York, you can't take a snapshot that was taken yesterday in New York and one that was taken 4 months ago in San Francisco and put them together and expect to get something meaningful. So how do you do this? It's a problem of synchronizing these photographs. And there are a number of problems real-life problems that can be solved if you can take pictures like this. The example I'll be giving is, of course, how much money is in the bank? There's a question that the bank president would like to answer. Of course, this is a rather toy example, but there are real problems that come up into building distributed systems, like is this system deadlocked? That's something that is a question that you can only answer from a global snapshot. And somehow you have to piece together a bunch of local snapshots in order to decide if that's the case. Well, the question that comes up is what constitutes a good snapshot? And to look at this problem, let's take a look at, this is a sample execution of this system. Time runs from bottom to top for various historical reasons. Here we have the 3 processes. They start with this configuration, $90 in branch A, $75 in branch B, and so on. The first event that happens is B sends $10 to C. So $10 is debited from bank B, and a $10 message goes out heading towards C. Then the next thing that happens is A sends $20 to B. So A's amount is, this send event causes A's balance to go down by $20 and a $20 message to go on this. And the next event is we missed something, an internal event here where there was an add $30 event in bank C. So C sort of spontaneously changed its state by adding $30. Of course, this internal event would correspond to some customer coming in and depositing $30 in the bank. But that's what I'll call an internal event, because from the point of view of this picture, it's just something that happens spontaneously inside of process C here. And then there's a receive $10 from C, does a receive 10 from B action, and so this $10 message is received, and the $10 are added to process C's state. Okay, this is a very simple-minded example, and it's a very simple-minded model. Now, what constitutes a good picture and what constitutes a bad one? Well, here is clearly a good snapshot. Here I've shown, we won't worry about how you take snapshots of the transmission lines yet. Imagine somebody in a plane somewhere over Iowa taking a picture of the transmission line between San Francisco and Chicago. So this is a perfectly good snapshot. You send this collection of 5 snapshots to the president, and he puts them together and can count up all the money and decide that exactly how much money is in the bank. On the other hand, here's an example of a bad, such a good snapshot, it was stolen. Oh, here we go. Here's an example of a bad snapshot. So notice that we've taken all of these snapshots at the same instant, but we've caught process A after this send22B event. And notice that this is a bad snapshot because $20 is missing. We caught this transmission line before the sending of that $20, so the $20 doesn't appear on this transmission line. But we've caught process B after he sent the $20. And so if you collect up these photographs and send them to the bank president, he's going to think that there's $20 missing, that there's $20 that are really in the bank at that time that didn't show up in this photograph. Okay, is everybody happy that this is a bad snapshot? It's an out of focus picture of the bank. Well, how about this one? First glance, it looks even worse than the last one because, we've got 2 events that happened between this send and between when these 3 snapshots were taken and when these 2 were taken. But let's look at this a little bit closer. This event happens in San Francisco. This event happens in New York. Now, they might have happened about 20 nanoseconds apart. And if they really happened very close together, there's no way we could really expect any algorithm to decide that this event had occurred before that event. But notice, if the events had occurred in the opposite order, then this snapshot would show exactly what the state was after this receive 10 from B event and before this after this receive 10 from B event occurred in process C and before the send B20. You see, if we switch these events out of order, then these happen after the receive 10 from B. These 2 were taken before the send B20, and the state of Chicago is unchanged by those 2 events. So this snapshot shows exactly what you would have seen had those 2 events happened in the opposite order, and the snapshot was taken from the moon after the receive 10 from B, but before the send B20 event. And since there's no way, if these events actually happened a few microseconds apart, there's no way to be sure in practice of telling that this was the order that they occurred. That would have to be accepted as a perfectly reasonable snapshot. Andrew, do you have a question? Just stretching your arm.
I'm wondering whether you were to rely on commutativity, but decided you were.
Mm-hmm. Well, they actually are commutative, but it's in fact why you can't tell from this picture, which is what makes it a perfectly good snapshot. Okay, well, so the whole major part of this talk is describing what is a good snapshot and what's a bad snapshot. And once we can answer that question, an algorithm for taking a snapshot will be simple. Okay, please feel free to ask questions anytime. When I see a sea of faces, I can't tell whether you're puzzled or bored. It's a problem I have with this talk. It can be either boring or puzzling to the same, it can be both, in fact, to the same audience. Okay, now the sort of picture that I drew here for this kind of picture is one way of viewing the system. In fact, what did I call it? Well, I've forgotten what name I've given it, but I'm sure it's written on a further slide. But it's a way of viewing the system, the execution of the system, as a sequence of operations. First this event happens, then this event happens, then this event happens, and looking at the state globally and just thinking of it as a sequence of states with events that take you from one state to the other. Now, let me draw another picture of this same execution a little bit differently. And this is called a space-time diagram because it looks a lot like the things physicists draw and call by that name. And this is the same thing. I've drawn the processes as these black lines. I've written the state of the process next to the line. The events are the dots, so that here's the starting state, same starting state, 90, 75, 50. Here's a send $10, a send C $10 event in process B. Here's that internal add $30 event in C. Here's the send B20 event in A, and so on. And here's that receive 20 event. And I'll show a few more events here. It's a little easier to draw, a little more compact. So this is another way of drawing that same sort of situation where to go from one model to the other, we just take this line and we cross an event, and that changes the state. And here's the next event we cross, and state changes, and so on. However, this is what the system looks like from the moon. Somebody who can see the whole thing at once. What do we actually see from here on Earth? Or, well, someone in San Francisco sees this. He sees what's happened in San Francisco. He sees that he started with $90, and he sent $20, he sent $10, here he received $5. And similarly, this is what Chicago sees, and this is what New York sees. And so what we have here are a batch of local histories. We see this nice piece of the state space-time diagram, the part of it that occurred at the local state. Now, the first thing we observe is that, switch to another projector, not every set of local histories is a possible system history. And for example, consider this, these two local histories. Here we have something that at first glance may seem perfectly reasonable. Here's one history has a received $5 event and a send $10 event, and this other history has a received $10 event and a send $5 event. So it's quite clear, one guy sent $10 to the other, and the other guy received, sent $5. $10 went in one direction, and $5 went in the other direction. But if we take a closer look, we see that this is really impossible, because this receive of $5 happened before the send of $10. But this send of $10 happened before this receive of $10, which happened before this send of $5, which happened before this receive of $5, which is, so this receipt of $5 had to have happened before itself, which of course is impossible.
Everybody does it all the time.
Pardon me?
E.F. Hutton does it all the time.
So the first question we have to ask is, what conditions must a set of local histories satisfy in order to be able to put them together and form a coherent set of local histories? Or rather, what conditions must the local histories form in order to be able to paste them together into a possible single system history? And there are two answers to the questions which depend on our two ways of looking at things. The first method, which I see is called, the first view, which I see is called the interleaving view, which is this one, the one where we view the system as a backward sequence of states, is that system history consists of a batch of local histories together with an interleaving. In other words, we want to take these local histories and form them into an interleaving history like this. Well, what we have to do is we have to take all of these and say that all these events must have occurred in some order. So there has to be some ordering of the events. So we sort of stack them all up, all these local histories up on top of one another. And you should sort of think of these as being sheets of rubber so that you don't know exactly how long the time is, because the actual distance is the real time that occurred between these events. And since we don't have any clocks, nobody is sitting there in San Francisco with a stopwatch, there's no way of telling how much time actually transpired between these events. So think of these as being sheets of rubber. So we have to stretch and shrink these sheets of rubber and put them together in some nice way so that these events are consistent with a global state. Well, what does that mean? Well, we assume we know what state we started with. And let's try to, how would we reconstruct a picture like this from a set of events like this? Well, it's fairly straightforward. Here we say this send 10 occurred in process B. Okay, well, we changed the state of B by subtracting $10 and add a $10 message to the transmission line from B to C, and so on. And everything will work out fine until we get to a receive event. And in order for it to work, we can always do a send event. That just puts something on the end of a transmission line and decrements the state, and we can always keep track that way. When we get to a receive event, when one of these things says, here we get, where's a receive event? Oh, here, we get a receive $20. This is an event in process B that says receive $20 from A. Well, that means for that to work, for that to be consistent, the head of the queue of messages from A to B must be a $20 message. So for this to be a possible set of local histories, a consistent set of local histories, we have to be able to find a total ordering of all these events, line them up in some way, and keep tab of the global history. And when we do it in such a way that when we get to a receive message, the right thing has to be sitting on the queue of messages. So that's the interleaving view of things. Okay, now let's take a look at the space-time view. Space-time view, a system history, we start with a bunch of local histories. So what we want to do is go from this picture to this picture. Well, how do we do that? Well, to do that, we have to connect the lines. We have to take, for each send, we have to connect it to a receive of the same value. So what that means formally is a one-to-one correspondence between send events and receive events. And of course, that has to have the obvious property that a send of $10 from A to B must be matched with a receive of $10 by B from A, so that the actual messages match up. But that's not enough, as we saw in the example, which has now vanished into the morass of in front of me, where we had the case, here it is, in this example, where we had a one-to-one correspondence between sends and receives, but it wasn't a possible set of local histories. And the extra condition that has to be met is that a certain relation, which I'll call arrow, is acyclic, where arrow is the transitive closure. Arrow represents the precedent, the temporal precedence relations that have to exist. And what are those temporal precedence relations? Well, temporal precedence relations include the ones that occur in an individual process. The individual process, we have an ordering of events within that process. We know that this event happened before this event, which happened before this event. And the only other temporal ordering we know is that a send event has to have occurred before the corresponding receive. I mean, you have to send a message before you can receive it. So we take those two sets of orderings, we take the transitive closure, and if that's acyclic, if that precedence relation doesn't have any cycles, then this is a valid set of local histories. Okay, so we have these two definitions of what it means for a set of local histories to be consistent, to form a possible global history. What's the relation between those two views? Well, if we have an interleaving history, well, what's an interleaving history? It gives us, from the interleaving history, we can sort of look at what event, send event, put a message into a queue. We can keep track of that message and see which receive event took it out of the queue. And so that defines a one-to-one correspondence between the sends and receives. And the first 30-second theorem is that this defines a space-time history. In other words, that one-to-one correspondence between the sends and receives that you get this way satisfies this definition of the space-time view. By a 30-second theorem, I mean that this is a theorem that you would sit down and scratch your head about, and in 30 seconds come to the conclusion that it's obvious from the definition, and then it'd take you somewhere between 5 minutes and 3 hours to write it out in all sorts of formal detail if you wanted to submit it to some place like JACM. Or it will probably take you about 2 minutes to explain it to your 11-year-old son. Okay, now conversely, supposing we have a space-time history. Well, a space-time history gives us a bunch of the local histories together with a partial ordering, that arrow relation that comes from the one-to-one correspondence between sends and receives. Well, space-time history says that this is a partial ordering, has no cycles, which means we can extend it to a total ordering. So we can extend that partial ordering to a total ordering. Well, that gives us a total ordering of the events. We can then take those events, total order them, and decide, does that total ordering give us a consistent set of global states? And in fact, the answer is yes. So that gives us an interleaving history. Yes?
Both of these views, given a particular set of local histories, there is any number of system histories that can include that, right?
Well, no. Starting from the interleaving history, there's only a single space-time history that we get to. But starting from a space-time history, there are lots of ways to extend an arbitrary partial order to a total ordering. So there are a lot of different interleavings, different total orderings we can get, which will give us different interleaving histories. But they will all of those completions will give us consistent interleaving histories. That is, the global states that that we get will make sense. Just as in the example, which is around here somewhere, that I started with, we saw that interchanging the order of these two events gave us a valid interleaving history. This execution order made sense. Okay, now we're trying to take a snapshot, which means to find a global state. Now, if we have an interleaving history, then we know what the global states are, because the interleaving history tells us at each instant, that is between any two events, what the global state is. But how can we talk about global states in the space-time view? Well, let me define a time slice of a space-time history to be a finite set B of events, which are called the before events, such that no event that's in B is preceded by an event not in B. And intuitively, a time slice, let me give an example. This is a time slice, the set of events that are inside this purple region. And you sort of think of the time slice as being the forward edge of it. You sort of think of the time slice as sort of the time after this event, and before this event. But formally, it's a set of events that occurred before that time slice. So this is a valid time slice. It's a finite set of events such that there isn't any event that's in the set that's preceded by an event that's not in the set. Here's an example of something that's not a valid time slice. Again, this is the set of events inside the purple dashed region, because here is an event B that's inside the time slice, the set that's preceded by an event A that's not in the set. Preceded because the send of a message precedes the receive of that same message. Because the arrow relation here is that transitive closure of the relation defined by the total ordering of events in each process and the send, precede, receive of the same message ordering. So this is a definition of a time slice, and an amusing little fact is that the set of time slices is closed under union and intersection, and they form a lattice, for those of you who care about such things. And it goes over big in academic audiences, but I sense that most people here don't really care that it forms a lattice. Anyway, fortunately, you don't have to worry because it's totally irrelevant to anything else I'm going to be telling you.
You tell a different joke in academic audiences.
Yes, in academic audiences, I say that they aren't really, the example of money doesn't mean too much to them, banks. Anyway, what is of interest is the notion of one time slice being earlier than another means that all the events in one are contained in all the events in the other. And intuitively, that means that if you look at if you think of the time slice as being the leading edge of this set, then earlier than means that that it lies strictly below, that one of these leading edges lies strictly below the other. They don't cross over. For example, here's a leading edge that's the time slice defined by this line, which are all the events underneath it, is later than this one. However, here's a time slice, two time slices that are incomparable, neither one being earlier than the other. Slowly, as this lecture progresses, the next slide gets buried deeper and deeper. And there's really an infinite set of slides here, but at some point I can't find the next one, and that's when I stop talking. Okay, now we have this notion of global states in a space-time view, and we also have the notion of seem to be missing a slide. Uh-oh. My goodness, it really has disappeared. The question is, what's the relation of... Oh, I see. Okay, this is... it's actually the bottom of this slide. Nothing lost. Okay. Now, how do we define the global state of a time slice? Okay, well, a time slice is a set of events. A global state consists of the state of a process and the state of each transmission line. And the global state of a time slice, of a process in the time slice, is the state of the process's latest event after the process's latest event in B. In other words, intuitively, let's think of the time slice being the set of points underneath this line. Well, the set of the state for that time slice is really the state of the line at which the state of the process where it's intersected by this line. So here we're the state after the last event that's in the time slice, which is the latest event. Let's be a little more interesting. The latest event, say in process B here, that lies beneath this line. The state is this one, and the state immediately after that says that there are $60 in the process. Now, the channel state, the sequence of messages on a channel, is the sequence of messages sent by events in B and received by events not in B. So, for example, here, another way of looking at it are the sequence of messages that intersect this line, that are sent by events underneath the line, events in the time slice, received by events outside not in the time slice, above the line. So that here's an example in which the set of states on the state of the channel between A and B consists of the pair of messages, this $20 message plus this followed by this $10 message. And in this state, there is nothing on the channel between B and C. Now, that's one definition of the global state of a time slice. Here's another definition. Choose any interleaving in which all the B events, all the events in the time slice, precede all the events not in B. In other words, take some interleaving, some total ordering, which is consistent with the partial ordering defined by the space-time view. Choose any one in which all the events below the line precede all the events above the line, and it can be shown, another 30-second theorem, that one of these exists, that at least one exists. Then we have an interleaving view, so that defines a global state after each event, and take the global state in the interleaving view after the last event in B. So in other words, we take some interleaving of these events. Of course, actually, you only have to worry about the events that happened before this time slice. We totally order them in some event that's consistent with the partial ordering defined by this picture. Say, first this, and so this is the last event. We put them into a sequence, we compute the state up to the point, and then we take the global state after this last event. And I claim, and that's another one of the 30-second theorems, that that's precisely the same global state that's defined by this blue definition. Okay, that's the theory. The algorithm should now be obvious. And since some of you are looking like you don't have anything else to do right at this moment, won't give it to you as homework, but I'll go through and develop the algorithm. To find a global, to take a snapshot, we have to take a global state. And to find a global state, well, you see, we don't have this interleaving view. What we have are the local histories. So we want to build our snapshot using the local histories, which means using the space-time view. So to take a snapshot, which means to find a global state, we have to find a time slice. So the trick is to find the time slice. I should mention, or I should have mentioned earlier, that in order to take a photograph, I'm going to have to add there has to be an algorithm here, and messages have to be sent. And I'll have to add some state information, and I may have to send some extra messages. But those messages that I'm sending and the state that I'm adding to the processes isn't part of the system. That's part of the camera, and it's not supposed to appear in the photograph. That doesn't appear in the snapshot. What appears in the snapshot is the state of the original system. Now, this description of this snapshot is due to this way of describing it is due to Dijkstra. I'll start by adding an extra state component, which is a color. There's the Dijksterian influence. Color will be either white or purple, and actually this is very different from Edsker's explanation of it, in which he uses white and red. And initially, all processes are going to be white. The extra action that I'm going to change is going to be a color change. That means to each extra action to each process, I'll add an extra action of changing color from white to purple. And now a little bit of definitions. I'll let the color of a system action be equal to the color of the state at which that action takes place. And since color changes aren't system actions, the color of the state, the color of the process when it does a system action is well defined. It's either white or purple. It's not changed by the system action. And the color of a message will be the color of the event that sent the message. So a white message is one that's sent by a white process or by a white event, and a purple one is sent by a purple process or purple event. And here's an example of this. Here are the should have known that one pen wouldn't be enough. Oh well. Here's the one turn purple event. Here's the turn purple event in process B. Here's the turn purple event in process C. These are white messages, and these are purple messages. They're sent by purple events. Okay, now what we want is to make the set of white events be a time slice. And what do they have to be a time slice? Well, to be a time slice, we have to make sure that no event in a time slice is preceded by an event that's not in the time slice. So to make the set of white events be a time slice, we have to make sure that no white event is preceded by a purple event. Well, how can a white event be preceded by a purple event? Well, a white event can't be preceded by a purple event in the same process, because the process just goes from white to purple and never turns color back again. So the only way you could have a process, a purple event preceding a white event, is if there is some message that goes from a white process to a purple one. Or another way of saying that is the set of white events is a time slice if and only if a white process never receives a purple message. And this isn't completely self-evident, but that's something you have to spend at least 15 seconds thinking about to convince yourself of it. Okay, then let's recall the definition of if the set of white events does form a time slice, what is the global state determined by that time slice? Well, the state of the process is the state after the process's last event in B. Well, so the process state is just going to be the state of the process at the color change event. And remember, since the color isn't part of the process state that we're photographing, it stays the same. It's not changed by the color change event, which only changes the color. The channel is the sequence of messages sent by events in B, sent by white events, and received by events not in B, received by purple events. In other words, it's just the sequence of white messages that are received after a process turns purple. Okay? And now, here is the the brilliant algorithm. Here's where what turns it from a theorem into an algorithm is that we don't actually color the messages. Instead, we're going to send an extra marker message on each channel that says all future messages are purple. Okay, once we have that idea, we can write down the algorithm. And being a nice structured algorithm, it's defined in terms of a subroutine, the go purple subroutine. A process executing go purple does the following. It sets its color to purple. Then it records the process state. Then it starts recording messages on all incoming channels. In other words, it has a tape recorder sitting at the bucket of each incoming channel, and it goes around and turns on all those tape recorders and starts them recording anything that comes in on the channel. Then, for every outgoing channel, it sends a marker message on the channel. Except this is a nice, laid-back, mellow California algorithm, and it doesn't have to do it right away. It just has to remember that sometime, anytime it wants to, but it's going to send a marker message on that channel, but it just has to make sure that it does it before it sends the next real system message on that channel. So it has to do it eventually. I mean, it has to can't be too spaced out. It has to do it at some point, but there's no rush. Anytime, just as long as it does it before it sends out any real system message. Okay, so that's the subroutine, the go purple subroutine. And here's the algorithm. A white process, anytime it feels like, it can execute go purple. So any process executes go purple when it decides it likes to initiate the taking of a snapshot. Okay, then the only other thing I have to worry about is what happens when a process receives a marker message. And when it receives a marker message, it does the following. If its color is white, then it executes the go purple subroutine. After doing that, it then stops recording messages on the channel over which it got the message. So in particular, if it started out being white, when it executes go purple, it's going to turn on the tape recorder on all the channels. And then the next thing it's going to do is it's going to turn off the tape recorder on the channel on which it received the marker message, which means that tape is going to be empty. Okay, now the algorithm is finished when every process is purple and has stopped recording on all its incoming channels. And another 30-second theorem says that implies that there aren't going to be any more marker messages that are in transit. Now, the next 30-second theorem says that this algorithm will eventually finish if any process executes go purple. Once some process decides to execute go purple, then eventually those marker messages are going to get around and be propagated throughout the network. I should say that I'm assuming that the network is strongly connected. There's a path from one process, from every process to every other process, but not necessarily a direct path, a direct link.
Is that a valid assumption?
Pardon me?
Why is that a necessary assumption in a system?
Well, it means that everybody can send a message to everybody else. That's the assumption. Obviously, the banker in Chicago is going to have trouble finding out how much money is in San Francisco. There's no way for the vice president in San Francisco to send a message to Chicago. Now, the global state is equal to, well, what do we have when everything is stopped? Well, everybody has recorded his own state He did that with the Go Purple subroutine. And everybody has a handful of tape recordings, one for each incoming channel. So there's a recording for each channel. And the global state is, in fact, equal to the recorded process states plus the message plus the message sequences. So every process has taken its own snapshot of its own state when it executed Go Purple, and the snapshots of the transmission lines are actually contained on the tape recordings. And why is that the case? Because, as we saw, the global state was equal to the process state is the state at the color change event. And in fact, that's exactly when the process recorded his own state, when he executed Go Purple. And the channel are the sequence of white messages received after the process turns purple. Well, the process turned on his tape recorder immediately upon becoming purple. And he turned it off when he got the marker message. And the marker message says that you've seen the last white message on this channel, and every other message that comes, every future message that comes in is going to be a purple message. So that tape contains exactly the set of white messages that were received by this process after it had turned purple. Okay, well, unfortunately, the information isn't sitting at the bank president yet. It's sitting at all the way around the network. And so the recorded information has to be gathered. And how you do that really depends on the application. In this example, if the bank president really only wants to know the amount of money in the bank, not particularly where it is, you don't have to send him all the pictures and all the tapes. What you do is each bank president just totals up the money that is in the snapshot of his state and in all the messages on all of his tapes, and just sends that dollar amount to Chicago. He doesn't have to send the whole collection of tapes. And similarly, in any time when you take a global snapshot, you're trying to find not really a picture of the whole state, but some function of the state. And so usually you don't have to send everything you've got. You can do some sort of collecting and compressing of information as it trickles through to the one site that's trying to get that to gather that global information. Well, the slides are almost buried. Okay. What good is a snapshot? Well, a snapshot is good for finding a stable property. I mean, a snapshot, by the time the president in Chicago has gotten the picture of how much money is in the bank, 47 deposits and withdrawals have gone on. So he's not really seeing the state of the bank at the moment he looks at the snapshot, but he's going to be seeing it at some previous time. And in fact, as we saw in the example, it may even be some bank balance that never really existed at any time. But it's in some sense a valid one, which might have, in some platonic sense, might have existed. What good is it? And what good it is it's good for determining stable properties. And a stable property is a Boolean function of the state such that, and I'll give you two characterizations of it. In the interleaving event model, it's true, a stable property is one that if it's true, then it's left true by any event. And in other contexts, this is called an invariant. In the space-time model, it has the property that if a time slice B is earlier than a time slice B prime, then if it's true on the global state of B, then it's true on the global state of B prime. An example of such a property is deadlock. A stable property is one that once it becomes true, it always remains true. And that, by definition, is what deadlock is. Once you're deadlocked, you're deadlocked. And the properties of that this algorithm have, and they're easiest to state in the interleaving view, is that if the snapshot shows a stable property is true, then that property is still true now. In other words, even though some parts of this snapshot that the bank president is looking at were really taken 4 days ago, if that snapshot shows that the stable property is true, then it's still true when he looks at the photograph. And conversely is if the property is true at some time, and remember, now is a meaningful concept in the interleaving model because there's a total ordering of events, and you can think of the state, global state at any instant. If the stable property is true now, then any snapshot that started now or later will show that property to be true. So first property says that if the snapshot shows it's true, then by God it is true. And the second one says that if this property is really true, then if you started the snapshot after it became true, then the snapshot shows that it is true. Well, this is a fairly simple-minded picture of things because, well, for one thing you might use an algorithm like this for is to detect deadlock. Well, you don't just detect deadlock so that you can say, well, system is deadlocked, sorry, we can all go home now. You detect deadlock in order to break it. Well, if deadlock can be broken, then it's not really deadlock, that is, it's not a stable property. So you have to be a little bit careful about how you use it. And of course, this is an idealized picture of the algorithm. You could initiate a snapshot algorithm anytime that you thought